Have you ever stopped to think about what's actually happening when you flip on a light switch? It feels like a little bit of everyday magic, but it's really just a beautiful, logical system. So today, we're going to pull back the curtain on that magic. We're going to build a simple circuit right from scratch to see how it all works. Let's dive in.
So, this is the big question, right? This is our goal. And to figure it out, we're not just going to talk theory. No, we are going to actually assemble the essential parts piece by piece right here and see what it takes to get that glow.
Okay, first things first. Every project, no matter what it is, has to have a starting point. And for us, for our circuit, that's the power source. Because without some juice, without some energy, well, nothing's going to happen.
And for our power source, we're going to use the classic electric cell, which, you and I would just call a battery. Its job is simple, but it's pretty brilliant. It takes all this potential energy that's stored up in chemicals and turns it into the electrical energy that we can actually use.
If you look at one of these things, it's actually super simple. You've got two main connection points. The positive terminal, that's the little metal cap, the plus side, and the negative terminal, which is the flat metal disc on the bottom. And inside, you've just got chemicals that are reacting with each other to make electricity. Of course, once those chemicals are all used up, the cell stops working, and it's time to get a new one.
All right, so we have our power. Component number one is sorted. Now, let's bring in the whole reason we're doing this, the light bulb. This little guy is what's going to show us if our circuit is actually working.
Now, the real heart of the bulb is this tiny, super delicate little wire inside called the filament. This is where all the action happens. When electricity flows through this specific wire, it gets super hot and starts to glow, and that's the light we see. It's really the star of the whole show.
And hey, just like our battery, the bulb has two terminals too. These thicker wires, they do two things. They hold that fragile little filament in place, and they act as the contact points for the electricity. One of them connects to the metal casing at the base, and the other goes all the way down to that small metal tip right at the bottom. Now get this is absolutely crucial. They are designed so they do not touch each other. Tuck that away, it's going to be important in a minute.
So we've got our power source, we've got our light bulb. Now for the million-dollar question, how do we actually connect them to make the light turn on? Because I can tell you, just touching them together any which way isn't going to cut it.
Well, the secret, it lies in this idea of a circuit. I want you to think of it like a racetrack. The electricity is like a race car, right? And that car can't get anywhere. It can't complete a lap unless it has a complete, totally unbroken track to drive on.
And that's exactly what an electric circuit is. It's a full, uninterrupted loop. It lets the electricity travel from one terminal of the battery, go through our light bulb, and then travel all the way back to the other terminal on the battery. It has to be a complete path.
Now, just so we're all on the same page, there's a rule of thumb for this. When we talk about the direction of the current, we always say it flows from the positive terminal out through the circuit and back to the negative terminal. That's just the agreed-upon direction for our electrical racetrack. And a fuse bulb is the perfect example of why this complete path thing is so important. In a good bulb, that filament is totally intact, right? It completes the circuit. But in a fused or blown bulb, that tiny little wire has actually broken. That one tiny break creates a gap in our racetrack. The path is incomplete, the electricity has nowhere to go, and so it can't flow. No flow, no glow. Simple as that. Okay, we did it. Let's say we've connected our wires from the cell to the bulb, and hey, the light is on. Awesome. But having to physically disconnect a wire every single time we want to turn the light off, that's kind of clunky, isn't it? There's got to be a better way to do this. And of course, there is. This is where the switch comes into play. Think of a switch like a drawbridge on our electrical racetrack. It gives us a super easy and really safe way to either open or close the path whenever we want. Because at the end of the day, that's all a switch really does. It's a pretty simple device, and it has one job. Either complete the circuit so electricity can flow, or break the circuit to stop the flow dead in its tracks. Think about it. When the switch is in the off position, our drawbridge is up. The circuit is open, there's a gap, and no current can get across. But when you flip it to the on position, wham! The drawbridge comes down, a piece of conducting metal closes that gap, and the circuit is complete again. The current flows, and our light comes on. So simple, but so effective.
This brings up another really good question. We use metal wires to build the path, right? But they're almost always wrapped in a coating of plastic or rubber. So why is that? Why does one material work so well for the path, while another one is used to protect us from it?
Well, it all comes down to choosing the right materials for the right job. And basically, all materials fall into two main categories. You've got conductors and you've got insulators. Understanding this difference is absolutely key, not just for making a circuit work, but for making it safe.
And the difference is actually really easy to get your head around. Conductors are just materials that let electricity pass through them super easily. They're the pavement for our racetrack. Insulators, on the other hand, are materials that do not let electricity pass through them. They're like the big safety barriers along the side of the track.
So let's look at some real-world examples. Copper is a fantastic conductor. That's why pretty much all electrical wires are made of it. Now, rubber and plastic are great insulators, which is why we use them for wire coverings and the casings for plugs and switches, to keep us safe. But check out these last two. Tap water and, yes, the human body are also conductors, and that is exactly why we have to be so careful with electricity.
And this, honestly, is the single most important safety lesson here. Because your body can conduct electricity, you can accidentally become part of the circuit if you're not careful. This is why we have insulators and why you always have to be cautious when you're handling anything electrical. So if we boil this all down, if we really think about it, building a working, safe circuit comes down to just these three things. You need power from a source like our cell. You need a complete, unbroken path made of conductors for the current to flow through. And you need control, using things like switches and insulators to manage that flow and keep everything safe. You know, from the simplest little flashlight to the most complex computer in the world, these three rules always apply: power, path, and control. So now that you know the basic blueprint, the fundamental rules for harnessing electricity, what would you want to power up? What would you bring to life?